Thank you for coming. I'm Zheng from Microsoft Research. So in the coming 50 minutes, I will introduce about how we can use big data and AI technology to solve urban challenges like traffic congestion, energy consumption, and pollution emissions. As we know, the rapid progress of urbanization has modernized many people's life, but also generated a lot of issues. Energy consumption, air pollution, and traffic congestion. So this challenges seems nearly impossible years ago, given the complex setting of the city. But recently, we have a lot of data generated, and we have a cloud computing infrastructure, which enable us to solve the big challenge in big city by using the big data, if used correctly. Okay. So motivated by the opportunity, we came up with a vision on urban computing since 2008, which is comprised of 4 layers, from urban sensing to urban data management to urban data analytics and service providing. Then we connect the 4 layers into a loop for a recurrent and unobtrusive improvement on people's life, city operating system, and the environment. So in short, we are going to use big data and AI technology to solve urban challenges. So in this conference, because we are data mining, so I focus on the 2-layer, data management and the data analytics. On data management layers, we need to look at 3 issues. First thing is spatial temporal data, which is unique. It's different from text, from imaging, from video data. And second, the platform. It's not a simple cloud computing platform. We should enhance current cloud computing platform to better support spatial temporal data. Third, we need to care about the spatial temporal indexing structure and combine the spatial temporal indexing structure with the cloud computing platform. So that's 3 issues I want to mention here. First thing is the data. We have a diversity of data in city generated every day. It seems that we have tons of types of data. But in terms of data structure, there are only 2 categories. One is called point-based data, another one is called network-based data. And further, according to the spatial temporal dynamics associated with each type of data, we can divide the data into 3 columns, which is called spatial temporal static, spatial static temporal dynamic, or spatial temporal dynamic. So let me elaborate on with a concrete example. For example, point of interest data is type of point data in a location. Once a POI has been built, for example, a restaurant has been built, its location does not change over time, so we call it spatial static. And the property associated with the building does not change over time. For example, the number of windows, the size of the building does not change over time either. So it's called spatial and temporal static data, point-based data. For some IoT data, Internet of Things data, although the location of a sensor is fixed once we deploy it, but the reading generated by sensor changes over time, every hour, so it's called spatial static but temporal dynamic, point-based data. For some cloud sensing data or Uber request or DD request, it's kind of spatial temporal dynamic data. We can generate request at 2 p.m. in one location, and another user may issue another request for taxi in another location and another time interval. So there's a spatial temporal dynamic here. Road network-based data is type of graph data, but spatial neural network is fixed and static. Once we overlap traffic onto the road network data, it becomes spatial static but temporal dynamic because the traffic on each road segment changes over time. What's the spatial temporal dynamic and the network-based data is trajectory data because there's a connection between each 2 consecutive points generated by one moving object. The difference between the trajectory data and the cloud sensing data is there is a connection between 2 consecutive points, but there's no connection between any 2 points in the cloud sensing data. So trajectory data is the most complicated but the most informative data set in spatial temporal data. So we have a tutorial on trajectory data mining, which was published at TIST in 2015. So you can know how we can do trajectory pre-processing, like the noise filtering, do trajectory segmentation, do state point detection from trajectory, and do back matching and trajectory compression. Then we can manage the trajectory with some indexing structure and query trajectory based on the indexing structure and some retrieval algorithms. And further, we have a trajectory privacy preserving algorithm, and on the other hand, we try to reduce the uncertainty in trajectory data. And also we have some trajectory pattern mining algorithm, for example, mining sequential pattern in trajectory data, mining periodic data, pattern from the data. And also we can mine anomaly from trajectory data and do classification for trajectory data. And also we can turn trajectory into matrix and then turn trajectory into tensor or graph. Then we can apply some tensor decomposition matrix factorization technology to solve the problem in trajectory data. So you can go through the survey paper for details. We release a slide deck in a PPT format on my homepage. You can download for free. There are about almost 1,000 slides. Okay. What to mention is the platform. On one hand, we have a diversity of data generated by different data sources, and the data set is huge and come in a real-time manner. On the other hand, we have a city-scale application to enable. It's not a prediction on a single road segment. It's a prediction throughout the entire city. So how to bridge the gap between the data set we receive and the application we're going to enable? The most intuitive idea is use cloud computing platform to bridge the gap between the two sides. But current cloud computing platform cannot support spatial temporal data very well for the three reasons. The first reason is the data structure is different. Spatial temporal data is very unique. For instance, if we take a picture, once the picture was taken, the size of the picture is fixed, does not change over time. But the length of a trajectory keeps on increasing as a taxi traverses in a city. Okay, we don't know in advance the size of a trajectory before the taxi terminates at some destination. And second, the query is different. When we query for documents, we usually issue some keywords, and then we do keywords matching exactly or approximately. But in spatial temporal data, we usually issue some spatial temporal range query or k-nearness neighbor query. For example, retrieval the taxi of where can taxi run me in past 3 minutes. So this is a spatial range plus a temporal range. And sometimes we need to search the nearest gas station around me when I was driving. So this is a continuous k-nearness neighbor query. And such kind of queries are not well supported by current cloud computing platform. You have to do something yourself. And third, in urban computing, when you are really going to deploy something, you need to harness a diversity of data sets instead of a single data set. But how to fuse the knowledge from data across different domains? You need to have some hybrid indexing structure to manage data sets in different domains in advance. So such kind of hybrid indexing technology is missing in current cloud computing platforms. So based on these challenges, so we develop and deploy an urban big data platform in Guiyang City. It's a big data pilot city in China. We design 6 data model. In terms of data structure, there are 2 types of data, point data and the graph data. And second, in terms of spatial temporal dynamics, we have 3 columns, so 2 by 3, 6 in total type of data. The reason why we design the 6 data models, we try to reuse these data models to accommodate different type of data sets. We don't hope we have one new data set coming, we build another new model, then your system becomes very complex and not easy to scale up. But once we design the 6 type of data models, no matter what kind of data sets we received, we can accommodate them with one out of the 6 data models. Then we can reuse some component in our platform and make our system scalable. On top of that, we leverage the existing storage on Azure, like Azure Blob, Azure Table, and Azure SQL Server. We don't necessarily build everything by ourselves. Further, we design spatial temporal indexing structure for different type of data models. And we build hybrid indexing structure to manage data across different data sets. And then we integrate the indexing structure into the distributed computing environment like Spark, Hadoop, and Storms. Then we can provide upper-level machine learning algorithm with APIs so that they can access large-scale data more efficiently. Here I use two examples to demonstrate the capability of the data management platform, which combines spatial temporal indexing structure with distributed computing environment. So the first example is we try to deploy charging station in a city based on the trajectory generated by vehicles. For instance, in this given area, we are trying to deploy 5 charging stations for electrical vehicles so that 5 stations can collectively cover the maximum number of vehicles traversing them. So this is actually a maximal K coverage problem over trajectory data, which is NP hard. Even you can use some approximating algorithm, but it's still very small because the number of intersections in a given area is so huge, and the number of trajectories is huge. You have to do a lot of updating and approximation algorithm process. But now, personally, using traditional algorithm without a platform, it will cost you a couple of hours to generate one round of results. But now we can produce one round of results in a few seconds. Why the efficiency is so important here? Because when we're trying to deploy something like electric vehicles, there are multiple criteria we need to consider. Not only the total traffic volume you can cover collectively. There are other criteria we need to consider. For example, what if there's no free space to build additional station? What if there's no restaurant or shopping mall around these places so that we can accommodate people when they are charging their electrical vehicles? As we know, when we're charging our electrical cars, it may cost a couple of hours where people can go. If there's no facility to hold people, we cannot build such kind of charging station here. So in such kind of a situation, we can remove, let's see again the animation. Okay. Without such kind of facility infrastructure around the place, we can remove the results generated by the algorithm and keep the rest of them which are eligible and let the algorithm to regenerate another round of results. So this is actually a way to combine human intelligence with machine intelligence. So typically when we are trying to deploy a big data project in the real world, we need to knowledge from both sides. One is domain knowledge, another is data science. And typically there are two groups of people who don't know each other very well. Some domain experts know very well some criteria to deploy charging stations, but sometimes they cannot tell us what exactly the rule is because it's too complicated to express. Or even they can tell us a rule, we cannot incorporate all the rules in our model because this makes our model very complex and intractable. So the solution is we consider a very simple solution like the total volume of traffic we can cover based on the selected location. Then we can present the results to the domain experts. They can say, oh, this one is good, this one is not good. Then they can remove some location that is eligible. Then we can keep the rest of the results and let the algorithm to generate another round of results. Through such kind of interaction, we can bring human intelligence into the algorithm. So this is a interactive visual data analytics that allow people to interact with the algorithm so that we can integrate domain knowledge with computer science and combine human intelligence with machine intelligence. But if we were trying to interact with the system, efficiency is very important. If I give you a feedback, you need to give me the result immediately. I don't have patience to wait one more day until you can generate another round of results. So if you're trying to interact with such kind of slow system, you have no patience, then the interaction is not feasible. So this system, so that's the reason why the system published at some visual data analytics conference. Without the platform, we cannot do such kind of interactive visual data analytics. Another example is we're trying to plan bike lanes for based on bike sharing trajectories. So China used to be a country based on bike many years ago. But since 2000, I think many people tend to driving instead of riding bike. You barely see people riding a bike in major cities. Very, very few. Only in university you can see people riding bike. But since last year, since change or not, because of the new bike sharing system occurs, there are many stationless bike sharing system that allows you to pick up a bike and park a bike anywhere and anytime. So now there are huge bike riding demands generated in China. You can see a lot of new kinds of bike sharing system. If the bike lane is well planned, then you have a good riding experience. But if the bike lane is not well planned, as we know, the bike lane was planned for riding demand years ago, but now huge demand comes. You would see this phenomenon very common. People have to risk their life to riding in a traffic lane. But how to construct bike lanes is a very challenging problem because of the three reasons. The first, there are some constraints. We have a space constraint and budget constraint. We cannot build bike lane anywhere. The government has a limited money and resource. And also, if you have one bike lane planned and you have one traffic lane lost, so the total space is limited. So that's a constraint. And second one, we try to serve each individual rider as better as possible. And we also try to serve as many people as possible. There are conflicts between the number of people you can serve and the riding experience you can provide for each individual rider. This is a conflict. Third, we hope the bike lanes can be locally connected, even though they cannot globally connect in the city. So if we simply choose the top 100 most frequently ridden road segments by users, it looks like this one, which is broken. Such kind of design is not user-friendly. You cannot ride on such kind of a broken road network, bike lanes. And this one is more user-friendly. Although we cannot connect them into a huge network because of the resource constraint, but in a local area, they're connected, providing user with a better riding experience. So given the three constraints, this is an NP-hard problem. Of course, you can have some approximation algorithm, but it's still very time-consuming because there's a lot of candidates to generate. Now, fortunately, we have new bike sharing system that allow users to pick up a bike and drop the bike anywhere, and also the trajectory of riding experience has been recorded and submitted to the backend system. So we know where and when people have ride a bike. So based on such kind of data, we can better design bike lanes in cities. So this is our motivation and how we use the data to design bike lanes. There is a two-step approach. In the first step, we select, for example, top 1,000 road segments that have been frequently ridden by bike users based on the data we received, bike trajectory data we received from Mobike here with Mobike data. Then we do a clustering algorithm based on road network distance. We use some hierarchical clustering algorithm, clustering the road segments, top 1,000 road segments into K cluster. Here the number of K is defined by governments. For example, governments say, I want to build bike lanes in 5 areas. So in this case, K equals to 5. And remember, there's also budget constraint. The budget can be converted to the total length of bike lanes that can be built in a city. For example, the government only has money to build 30-kilometer bike lanes in a city, and they hope the bike lane can be built in 5 areas in total. So k equals to 5, and the budget constraint is 30 kilometers. Now, in each cluster, we select the most frequently ridden road segment as a seed, and then gradually expand the bike lanes in each cluster in a greedy manner. So this is a general idea of the framework. The motivation lies in 2 aspects. The first, intuitively, people's riding demands usually starts from some hotspots like subway stations. After you get off a subway, then you pick up a bike and ride to your destination. So people's riding experience usually starts from some hotspots and then expand to other locations. So it's a general expansion process. And on the other hand, if we don't do clustering, we just select the most frequently ridden road segment as seed, and then do expansion. Then finally, you will see the planned bike lane will only located in one area, because the top k frequently road segments may located in a single area. Then the expansion will be connected, and other location may not have bike lane planned. So that's the reason why we need to do cluster first, and then do greedy expansion in each cluster with the constraint. So clustering algorithm is very simple. It's kind of a hierarchical clustering algorithm. We cluster each individual pair of road segments based on their neural network distance, and then gradually aggregate them into k clusters in this way. So finally, we have a k cluster generated. Now then, in each cluster, we select the most frequently ridden segments as seed to start a greedy expansion, like this. The greedy expansion is based on an object function. The object function is defined as this form. Okay, in this form. So here, S is a segment covered by user's riding trajectory, and S.L means the length of the road segment. Alpha is a parameter larger than 1. When alpha equals to 1, also here we try why we design this score function, because we try to differentiate people's riding experience under 2 different designs. Our assumption is people prefer to ride on consecutive or continuous road segments, bike lanes, instead of a broken design. So for example, this is a trajectory, the blue dotted line is a trajectory generated by a bike riding user. So if we plan bike lanes in this manner, then this is a broken design. It's not user-friendly. People prefer to ride on a continuous experience. So in order to differentiate these 2 situations, we say this one is better than this one. We design our score function in this manner. When alpha equals to 1, the 2 situations is equal. But the bigger the alpha is, the more emphasis we put on the continuity. So that's just how we define the score function. Then I'll give you one example. For example, there are 2 trajectories generated by 2 different users. Then E1 is the root segment we have with the seed root segments we are going to start with. Then we will try from this root segment. We will do many expansion on different root segments. For example, we can try to expand E2. Then we will calculate if E2 is planned, what's the score will this design will obtain based on the 2 trajectory. So we can calculate the score in this way. If E1, E2 is planned, for trajectory 1, it covers the length E1.L plus E2.L. And this is the score that trajectory 1 obtained from this design. And for trajectory 2, it only covers this part. So it's only this way. Supposing the length of the 2 road segments is 0.1 kilometer, then we can calculate the score of the design. Then we can greatly try other expansion. For example, we try E3, E4, E5, etc. And finally, we find the root segment with the best increase of score, delta score, and divided by the total length of the root segments of backline you have ever designed so far. So this is a great expansion, but it's very slow. If you don't have some indexing structure and in parallel computing framework, it's very slow. So we combine indexing structure and the platform to improve this algorithm. And we will have a presentation for this research in this conference. We have a paper this year. So this is the results we obtained by analyzing the bike sharing data. You can see there are, I think they are centered by subway stations. We don't consider subway station when we do data mining, but it turns out they start with the bike subway station. And we can look at this one place, particular place. The red lines are root segments that we suggest to build bike lanes. But originally, there are only two lanes. There's a subway station, a shopping mall, and notable residential area. So people have a lot of riding demands in this area. But originally, there are only two routes with bike lane builds. So when people riding on the two routes, they can get a very good riding experience. But for other route segments, for example, the red ones, people have to ride on pedestrian roads or risk their life riding in a traffic lane. So this example, we can use big data and some AI technology to help our government to better plan our backlanes more effectively using limited resource. So this improves not only people's riding experience, but also try to avoid some traffic, and also it's good for some for the company's business. So it's a win-win situation between people, city, and the environment. Okay, for the data analytics layer, we need to look at 4 issues. The first one is how to adapt the machine learning algorithm that when originally designed for computer vision data, text data, image data, and to spatial temporal data. Because spatial temporal data is unique, and how we can adapt them. The second issue is we typically mine single data sets years ago in data mining area, but now it's time to mine multiple data sets simultaneously. How to fuse the knowledge across different domains? That's a problem we need to solve. And third, database and data machine learning used to be two separate communities. They have their own conference and all journals to publish paper. The overlap between the two communities is very, very minor. But in order to deploy urban computing projects, we need knowledge from both sides. How to fuse the knowledge from both sides to design algorithm. That's very important. And third, from simple static data mining to interactive visual data analytics. That's 4 issues we need to resolve for urban data analytics. This is a logical layer, and this is a physical layer. So this is the layer we just mentioned in our platform. On top of the data management layer, we have a data analytics layer, which is further comprised of 3 sublayers. The first sublayer is a common machine learning tools that every people knows, like decision tree, classification model, regression model. But this is general model. It's not good enough for spatial temporal data. And then we have to customize some machine learning algorithm dedicatedly for spatial temporal data. Then on top of that, we have some cross-domain knowledge fusion algorithm designed for spatial temporal data. So I will focus on the 2 layers and give you more examples. So first, why spatial temporal data is unique? Spatial temporal data is unique because it has spatial property and temporal property. In terms of spatial property, it has a spatial distance and a spatial hierarchy. So why spatial distance is very unique? According to the first law of geography, everything is related to everything else, but the near thing is more related to distancing. So we have a very strong correlation between the reading of 2 locations with a shorter distance than the 2 locations with a farther distance. You might say In computer vision, we also use distance to measure the correlation between two pixels. But the correlation between the two pixels is not that intuitive and not that meaningful as compared to the geographic distance. Let me give you one example. So for example, you can take a picture of me. Then on the 2D space of the picture, a pixel on my face and the pixel on the background that is close to my face is very close on the 2D picture, right? On the other hand, another pixel on my right face maybe have a farther distance to the pixel on my left face. But it's more correlated than the pixel right behind me. So using this example, P1 and P2, you can see they're very close to each other, but one on the background, on the face. Another one, P3, looks very far, but it's still on people's body. So when you are doing segmentation, P2 and P3 are more correlated than P1. So the distance, the meaning of the distance, that really hold in many computer vision scenario, but they have more meaningful. They're more meaningful in geographic distance space, and also we have some triangle inequality that can be used to prune some certain space, and you can barely find such kind of triangle inequality in some computer vision because the distance is not that very meaningful. And for hierarchy, spatial hierarchy, there's natural spatial hierarchy in our world. For example, a city is comprised of some districts, and further districts comprised of some neighborhoods. And so on different layer of the hierarchy, we will find different semantic meanings. It's totally different from merging the pixel layer by layer. So let me give you one example. So if we are trying to estimate the similarity between a pair of users based on their location history, we assume the more number of locations you shared in your history, then you two guys are more similar. Then how to define the location is a problem because locations have different granularity. You can say we share we share location in a room, or we share location in a city, or we can share location in a city. People share location in different granularity of location has different meanings. Each of them are useful. So in this example, if we don't have the granularity, we can barely differentiate U1, U3, U4, U2, U3, U4. If you only have one layer of information, we may say that this is too small to see. Let's say if we only have this layer, we see the green dots standing for U2 and the purple one standing for U3, and the red one stands for U1. If we only have this layer, without this layer, we cannot differentiate the three users. They look very similar because both of them start from this location and end of this location. But with the fine-grained information, we can say the purple one and the red one share one location, but the green one and the red one does not share any location. So we can say the purple one is more similar than the green one as compared. The purple one is more similar to the red one as compared to the green one. So that's the reason different layer of hierarchy will bring more information, more semantic information than pixel merge. So that's a spatial property of spatial temporal data. For temporal property, there are three subcategories. One is called temporal closeness. This is very common. For example, the traffic flow at the adjacent time interval may be similar. So this is very similar to the video frames. Two video frames that are close to each other may be similar to each other. But the periodic information in spatial temporal data is very unique. We have traffic repeat every day. We have flow of cars repeat every day. For instance, the morning rush hour of today may be very similar to that of yesterday. But the morning rush hour of today, for example, 8 a.m., is very different from the traffic condition at 12 p.m. today. Even if 12 p.m. has a 4-hour time difference than 8 a.m. But yesterday 2 p.m. and today's 2 p.m. has 24-hour time difference. but yesterday has a higher similarity of traffic condition than 12 p.m. today. So this periodic information breaks this one. So if we only consider this one, we will do not have false prediction. And also there's a rising trend or dropping trend in the spatial temporal data. The periodic information is not static, it's dynamic. For example, when the temperature keeps on decreasing, people are getting up early in the morning, then the morning traffic, morning rush hour comes early and early. Then you can see the rising trend of morning rush hour comes in every morning. So such information, such property is very unique, calling for different machine learning algorithm and data mining algorithm for spatial temporal data. So that's a unique thing for spatial temporal data. And second, for cross-domain data fusion, I summarize them into 3 categories. The first one is called stage-based data fusion algorithm. The second one is called feature concatenation, feature level-based knowledge fusion method. So which is further comprised of 2 subcategories. We can do some simple feature concatenation plus some regularization, or we can use deep learning to do data fusion. But deep learning is only one subcategory of the second category. And for the third category, we call semantic meaning based. In many cases, we may not have enough label data, or may not have enough label of training data. So we have to use other methods to fusion the knowledge from data across different domains. There are multi-view based learning method. For example, co-training is one example. And the probabilistic dependency based method, like graphic model, to fuse data across different domains. Or use the similarity based method, like a matrix factorization or context-aware tensor decomposition. Or using transfer learning algorithm to fuse the knowledge across different domains. So let me give you one concrete example. To demonstrate the deep learning based one, because time is very limited, I cannot go through all of them. I just bring up some new research because I give such kind of talk every year. I try to give you some new updates. So in this research, we try to predict the inflow and outflow of each and every region throughout the entire city based on spatial temporal data. So for example, we can divide a city by uniform grades, and I can predict the number of people entering a given region and departing from the region in over the next couple of hours. So the motivation of the research comes from public safety. In the January 1st of 2015, there was a catastrophic stampede occurred in Shanghai. Many people stepped into the bomb area to watch the light show, but the area is too narrow to hold them. As a result, many people got killed by stampede. But if we can predict the number of floors or the flow of people step into the region and departing from the region a couple of hours ago, then we can do traffic control or do evacuation in advance. I still remember the conversation with Hans-Peter Krieg. Okay, years ago we discussed the stampede occurred. You mentioned we can use cell phone data to predict, or even we can monitor the flow of people. That was in 2011 in San Diego, right? We discussed this topic. And finally, we have a better solution to predict the flow of people from each and every regress. So we deployed the system in Guiyang City. We partition the city into uniform grids, and we predict the number of test cabs step into a region departing from region. I'm not saying test cab can stand for flow of people, because test flow is only portion of a flow of people. I'm just using the test cab data to demonstrate the capability of the prediction model. So if you give me cell phone data, I can predict the number of people step into and departing from the region. Or if you give me bike sharing data, I can predict the number of bike riding into a region, from a region. And if you give me food delivery data, I can predict the number of requests in each region. So this is a very general model that we can predict flow, different kinds of flow. What kind of type of data you give to me, I can predict what kind of flows. So the application of the research lie in 2 folds. One is for public safety, I just mentioned. We can do evacuation at once. Then we can avoid some tragedies or disasters. And the second is for logistic industry, for a smart or intelligent scheduling. I believe AI has a better solution, can provide better solution in many logistic industry. I think there are some audience from this area. Here, I want to mention the challenge of this topic. It's not that easy because when we discussed this problem in 2011, it's about 7 years ago, but there's not a challenge we cannot solve at that moment. The first reason is the flow of people in a region depends on multiple factors. For example, the number of flow, inflow and outflow in this region in the past few hours, and the number of flow of people around these regions, in other regions around this region, in its neighboring regions. And also we need to consider the flow of people in regions that are far from the location we're going to predict. Because in some major events, people would take subway system, reach a destination location without passing its neighboring regions. If you don't consider the location that is far from the target location, you may not be able to predict some major events. If you only can predict some regular patterns, it's not useful. But if you want to consider the location, the regions that are far from the target location, this makes this problem very complex. That means you need to consider almost all regions to predict one traffic in one regions. This makes this problem very complex. Then if you are trying to use some graphic model, then this is very complex to solve. And also we need to consider weather condition and some events because they impact the flow of cars significantly. So that's a challenge. And also we need to consider the spatial temporal property of the spatial temporal data because they are unique, which means we cannot simply grab some deep learning model to apply to this problem. Now, how we solve this problem? First, we divide a city into uniform grids, and we project the traffic data we receive in the past few hours. This can be taxi trajectory data, or it can be cell phone data. We count the inflow and outflow in each grid at each time interval. Then we can formulate a matrix for each time interval. We can formulate a matrix with each entry standing for in and out. Just like a pixel with RGB, there are 3 channels. Here we only have 2 channels, in and out. This figure visualizes the outflow of each region. The lighter the region is, the more number of flows departing from the region. And we can imagine we have another inflow of images. So if we have multiple, we have data for multiple frame of time intervals, we can formulate multiple frame of images. Then we also have events and the weather condition at a different time interval. What we're going to predict is the next frame. What the next frame looks like. That means we can predict the inflow and outflow of the next couple of frames. That's our goal. And how can we design this model? It's not simple LSTM. It's not a simple CNN model. We solve this problem in this way. First, we threw the recently received a few hours into a deep residual convolutional neural network to model the temporal closeness. That means the traffic condition at adjacent time interval could be similar or change smoothly. And then we throw the same time of yesterday, for example, 2 p.m. of yesterday, 2 p.m. of the day before yesterday, and even a few days ago, 2 p.m., and throw them into a similar structure of deep residual convolutional network to model the pure information of the spatial temporal data. And also we through the same time interval of last week or even last month to model the the trend information. And then we can only use the couple frames and skip other frames. Then we can well capture this pure information, trend information, and the temporal closeness information of the data. Then we fuse them based on dynamic parameters learned from the entire framework. And we also do later fusion because events and weather condition may in fact impact the entire city instead of a single location. So we do such kind of fusion and finally predict the results. So here I want to emphasize it's a collective prediction. That means we predict each and every grace simultaneously and collectively because they are correlated. You cannot do individual prediction. So if you do prediction for each individual grades step by step, then you might say the total inflow of the grades may be greater than the total population of the city. So this is a collective prediction. How can we capture the spatial correlation? So in this module, we have a multi-layer deep convolutional neural network. As we know, when we do one layer of convolution, we capture the spatial correlation of near distance. Because you do convolution, you aggregate the information from the near neighbors. But once we do multiple times of convolution operation, it actually capture correlation between location with a farther distance. The reason why we need to consider farther distance, because I mentioned, when there are some major events happening, people will take subway, reaching the destination through underground channel without passing your neighboring regions. So you have to consider region from far distance. But when the layer of CNN becomes deeper, the training becomes very harder. Then we have to use a residual network to improve the performance. Regarding the aggregation, I said it's a dynamic aggregation. It's not static. It's not say 1/3, 1/3, 1/3. The three more components will generate prediction individually. We aggregate them dynamically based on this parameter matrix, which means for each grade, we will have its own three parameters to aggregate the three results. Apparently, different locations have different trend and periodical information. For example, I'll give you one. In some location, for example, like hospital, the period information is not very obvious because you cannot predict when you get sick, so it's more random. But in some zone or in some parks, you can see a very obvious periodic information patterns because people go to parks on weekends. So the weights of the three components may be very different in different places. Now, at this stage, we predict the inflow and outflow in each area. I mean the total inflow and outflow, but we are not satisfied with the results. The new research I'm going to present in the next slides. We can predict the transition between any two locations. That means we don't not only know the total inflow of the location, we also know where people comes from and where people live for. So that's a transition prediction. You can say we can predict the transition between any two locations. Sometimes it's no traffic between the two locations, but sometimes there's a heavy transition between them. This prediction is even harder, much more difficult than the inflow-outflow prediction because it's n-squared prediction. Supposing there are n grades, then if you only predict the inflow-outflow, the computing complexity is O(n). But if you are going to predict the transition between the n grades, it's n-squared, and the data is even sparser. Because in some transition, you might not have prediction data. So you need to learn how to encode the graph data in order to use deep learning algorithm. I will go back to say why we use deep learning here. Because sometimes say why not use LSTM? Why not use CNN? If you use LSTM, you're trying to capture some temporal information of the data. But as LSTM formula data is a vector, it does not capture the spatial correlation between different locations. So LSTM does not capture spatial correlation. And also, if you are trying to use LSTM to capture the trend information, you have to throw a long period of data as input. If your data is only have a couple of hours, then the data itself does not contain period information and the trend information. If you're trying to throw a 3 months data into LSTM, supposing we say 1 hour per frame, then 3 months data will generate over 2,000 frames for LSTM. LSTM with such a large scale cannot be trained very well. We tried this performance is very, very bad. And here we only consider a couple of frames. Here we consider the recent few recent few time frame and the frame of last day, the day before last day, and the last week, the week before last week. So we can make the training very effective. So that's the reason why we cannot simply use LSTM to predict the flow of cars. And also other models, we try some graphing model, cannot scale up to this level. As we know, if we partition city into 1 kilometer by 1 kilometer grids, there are over 3,000 grids in Beijing. It's huge, and there are a lot of connection between them. If you are trying to connect one grid with the rest of the grids, the graphic model is very huge, and it cannot be trained by the sparse data. So that's why we use deep learning. We use deep learning because we don't not only because we want to use deep learning, because it's truly applicable and useful here. We need to give a concrete reason. I don't hope people try to grab deep learning to solve everything. We still have our algorithm to solve something. We need use deserve it. Okay. With the transition data, we can better deal with some public safety issue, and also we can do logistics industry with some intelligent dispatching. For example, the algorithm actually have been used by mobile system. They are using our system to predict the inflow or outflow of bikes in a city. Then they can use trucks to reallocate bikes among different regions, because we know the demands and the requirements of bikes in different regions is highly skewed. In some locations, you may see a lot of bikes located there, but very few people riding them. But at other locations, you might see we don't have bikes ride, but many people request to ride. Okay, so you have to do prediction. Prediction is one step. The very preliminary step, you have to do prediction, then you can do reinforcement learning. So prediction is one step, and then deep reinforcement learning to optimize the reward for over a long period of time. Okay, and also this model can be applied to solve some food delivery service like 美团外卖、饿了么 and so on. Actually, we are working on this problem, collaborating with 饿了么. So this is even more challenging because there are two objects, like the user who order dishes and the deliverer who send the food to the users. And there are three locations to consider: the current location of the carrier, and the location of the user, and the location of the restaurant. Three locations, two objects, and there are 3 times to estimate. One is the travel time from the carrier's current location to the restaurant, and the second time is pick up time of the food. You need to wait for a while until you can pick up food from a restaurant. It's not like taxi, you can get people on board very quickly. Then there's additional time you need to wait. Okay, and third, you have to estimate that the delivery time from the restaurant to the user's home. So there are 3 times 3 location, 2 objects to estimate. And sometimes you need to dispatch them. You have to dispatch multiple tasks to a single person simultaneously. It's not a one-by-one dispatcher. Like taxi, we usually dispatch one rider to one taxi driver. And after finish this rider, then we dispatch another rider to the taxi driver. But here, sometimes we simultaneously deliver 3 packages to one carrier. So the order between the pickup and delivery is very complicated to estimate. And this is, I believe this is the most complicated problem in logistic industry. So we are solving this problem. This is a new update. So you can see, and also the travel time is very difficult to estimate, because when the carrier deliver food, they never respect the traffic lights. Okay, so you have to estimate the travel time based on their own trajectory. But what if there's a new location that has not been reached by any rider? How to estimate the travel time? It's a problem. Okay. And also, user demands come in a very dense period. For example, during the lunchtime, not all people issue query for food delivery. So there are millions of requests generated in 1 hour. You have to dispatch them very efficiently. So that's the reason why I say this is the most difficult logistic industry problem. Okay, prediction is definitely the first step. We predict the number of requests in each area. We know how many people would like to order food in each area in advance. Then we continue to do prediction, do reinforcement learning to optimize the dispatching logistic. Okay, so this is an application for this one. Let's see, this is our topic, air pollution. I have introduced this project multiple times, even at KDD. So I try to make it quick. So this is I think it's a global concern, majorly for developing country. It's a headache it's a headache of Chinese governments. Air pollution, you can see, is bad for people's health. And governments have deployed many air quality monitoring stations on the ground to inform people their ambient air quality every hour. But the air quality monitoring station is huge and expensive. It's not very small. And also we need to spend human resource to take care of the stations. So that's the reason why we cannot deploy such kind of station anywhere. In Beijing, there are 35 monitoring stations deployed within the 6th ring road of Beijing. This is a replay of the real data, where each icon stands for one air quality monitoring station, and the number associated with each icon means air quality index. The smaller the better, the bigger the worse. Green means very good, and the red means unhealthy. As we can see, even at the same moment, the air quality of different locations may be very different, even if the two locations are very close to each other. You can see these two places are close to each other, but the reading may be hundreds different. It's not surprising to see this phenomenon, as air quality is influenced by multiple complex factors, like traffic flow, source of pollution, and the density of building, what's the dispersion condition in the area. All this information are different in different parts of the city. So the problem is, if there's no monitoring station deployed here, what's the air quality of this place? We don't know that. So we try to infer the real-time and fine-grained air quality throughout the entire city based on two parts of big data. The first part of data is real-time and historical air quality data from existing monitoring stations. And second data source is further comprised of dataset is further comprised of 5 data sources, like meteorological data, like wind speed, temperature, etc., like traffic data, and human mobility data, like number of people departing from a region and entering in the region, and also the number of POIs, for example, the number of restaurants located in a given region, the number of factories located in the region. And also we consider the structure of road networks, such as the number of traffic lights in a region and the number of intersections, or number of the length of highway and the total length of service roads in a given area. So using a machine learning algorithm, we can build a mapping between the data we observed in the region and the air quality of the region. Once the model has been trained, we can apply the model to other places without a monitoring station. So finally, it looks like this way. It's highly nonlinear. Now, what's this fine-grained information for? It can inform government decision-making and people's trip demand planning. For example, you can see the air quality of anywhere, so you can plan where and when go jogging. And recently, we put together the data from a cluster of cities instead of individual cities. So the reason we put them together is when there's air pollution occurs, the problem might not lie in the city itself. With the fine-grained information of a class of city, you can see when air quality turns from good to bad, you can see where tends to be bad first, and then you can trace the source of air pollution. So that's a fine-grained information for. And this was a application at the KDD 2013, and finally deployed with Chinese Ministry of Environmental Protection in 2014, later 2014. And further, we are not satisfied. We are further forecast the air quality over the next 48 hours in each location. So this is a fine-grained forecast. I'm not saying Halifax is going to be good or not. I can tell you what's the air quality in a specific university at the next 6 hours or over the next 12 hours. So it's a spatially fine-grained or temporal fine-grained. And also there's an inflection point to predict, which is very hard. Inflection point means when there are some strong winds comes or rainstorm comes, the air quality of a location may drop from 500 to 50 in 1 hour, generating some inflection point. Being able to predict the inflection point is very, very important to inform government decision making. Because if we know tomorrow is going to be a inflection point, it's not necessary to do traffic control or pollution control. Then we don't need to shut down factory. We can avoid some loss because of the shutdown. Okay, and in 2000, this paper, second paper, was published in 2015 to forecasting, and finally deployed with Chinese Ministry of Environmental Protection in over 300 cities in 2016, early 2016. So there are two steps. First step, we understand the current situation in 2016 and deploy in 2014, and later we do forecast and deploy in 2016. Now you can see the majority of Chinese cities are using our technology from KDD conference. And now the final step, we just to get it done, we're trying to diagnose the root cause of air pollution. We look at the current situation, we forecast the future, and we look back at history, why there's air pollution, where does the air pollution comes from. I think it's very easy to tackle the air pollution in Beijing if we can shut down all the factory around Beijing. You can see clearly blue sky, but it hurts economy. How to tackle the air pollution with a minimal impact to the economy? That's a problem, and that's our target. So we are trying to identify the source, the causality paths of air pollutants among different locations. Then we can tackle the source. By plug out the source, we can tackle the air pollution fundamentally. So I'm not going to present anything here, but I tell you we have just get it done. The published paper, the TBD. We will do some promotion later. This one is related to energy consumption, urban planning, and the environment, because we can estimate or infer the gas consumption, pollution emission of vehicles throughout the entire city in the past 10 minutes in a real-time manner. Here we use a GPS trajectory of sample of vehicles. Here we just taxi trajectory data as input, and combined with point of interest data, the network data, and meteorology data. So this still data filtering methodology. So this is a real system we deployed in Guiyang City. It's real. I mean, the data stream into our system every seconds. We use our platform to do management and data analytics, do service providing. So you can see this is a traffic volume map. It's not a travel speed map. How to define traffic volume? Traffic volume means the number of vehicles traversing a given route segment in a given time interval. So let me ask you one question. If the traffic volume is high, whether the travel speed is fast or slow? I think the first answer came to many people's mind is slow, because we usually heard some news say the traffic volume is high, then travel speed, there's some congestion here, then you have to bypass this congestion. But if you can think about this problem, if there's traffic congestion, the number of vehicles that can traverse a given route segment is very few. If we get it completely congested, the traffic volume is zero. So on that hand, if the traffic volume is high, the travel speed must be high, and the density is not small. Travel speed, density, and traffic volume are three things affecting each other. So we don't really have a traffic volume map. What we really see on Google Map, Bing Map, there are travel speed, but you don't really know the number of vehicles traversing the given route segment in the past few minutes. But traffic volume really matters. it can inform people, governments' decision making on urban planning, how many traffic lanes we need, and also we can inform location selection. For example, if you want to build a shopping mall, you need to estimate the number of vehicles traversing this area, and also you can calculate pollution emission. For example, in Guiyang City, you can calculate the pollution emission of PM 2.5, carbon monoxide, carbon dioxide, or nitrogen monoxide in a real-time manner. By calculating the data, and also we can associate the data with the air quality data monitored by the station. Then we can infer what's the percentage of PM 2.5 was generated by vehicles in the city. This can inform government's decision making on pollution control. Is it really useful to do traffic control if we are trying to lower air pollution? This research can inform government decision making. And this was solved by context-aware matrix vectorization and some combined with some graphic model. I'm not going into the details. There are publication at the KDD 2014. So the majority of the example I present here was when published at the KDD conference and later deployed in China in real world. The last example is how to transfer knowledge between different cities. This is a very, very new idea. We typically see this phenomenon are very common. We have enough data in some major city, like New York City, like Beijing. We have traffic data, we have 311 data, we have weather condition data. But if we go to a small city or small town or a newly built city, this infrastructure was just built, or the data is very sparse, or just being collected. Our model cannot be used to that small city or new city. So can we transfer the knowledge we learn from the major city, which has sufficient data, to the city without sufficient data? If we can do such kind of transfer, we can solve some cold start problem in many smart city projects. So we call this paper Transfer Knowledge Between Cities. So we can imagine what we can transfer and what we cannot transfer. Apparently, we cannot transfer the model we train based on the data from source city to the target city directly, because the label distribution may be very different in the two cities. For example, the air quality of Beijing may be very different from Hangzhou. So we cannot grab the model trained in Beijing to infer the air quality of Hangzhou. That's impossible. And second, can we grab the data of Beijing, the traffic data of Beijing, to use it in another city like Shanghai? I think it's impossible because the city has different road network and different traffic patterns. You cannot directly grab the data from one city to another city. But what we can transfer? First, the relationship between the different data sources can be transferred, which is universal. For example, when there is traffic congestion, the air quality gets bad. The relationship between the traffic data and the air quality data may be universal and can be transferred between different cities. So the relationship between different data sets can be transferred. Second, although the data itself cannot be directly transferred to another city, but if we project the data into a latent space, in the latent space, two cities' data might have a similar meaning. For example, the traffic data of Beijing and Shanghai may be very different, but if we project them into a latent space, they might share the similar pattern. The pattern is during the morning hour and evening rush hour, there are traffic congestion, but during the rest of the time of day, there's no congestion. So they may share the similar representation, but by representing them into a latent space, we can use the data aggregately. So that's what we can share. I'll give you a more concrete example. In Beijing, for example, the air quality project, there are 4 data sets we use. In Beijing, we have sufficient data in Beijing, but in another city, small city, we only have 3 data sets. And even for one data set, it's very sparse. So for each data set in the source city, we call this source city, this target city. We try to transfer knowledge from here to here. We can extract a feature from each type of data sets, where each column stands for denotes one instance, and each column stands for one feature, and each block denotes one type of data set. So there are 4 data sets and 4 instances. Based on the data from rich data sets, to rich city, we can train a dictionary which encodes the relationship between different type of data sets, and also we can use the dictionary as a base to transfer to project the data from different city into a latent space. For example, we can project data into a latent space through sparse coding and using the dictionary as a base. Then we can put together the data from different city to train a model. I'm not going into the detail, but you can read the paper for details. So finally, I want to show you one slide. Data scientist. This is my favorite slide. Typically I use this slide to end my talk, because when you are going to do urban computing, you must need to know what kind of skill a data scientist need to be equipped with, and what's the difference between a data scientist with data analyst. We have we see many advertisements trying to recruit data scientists, but according to the requirement, they're trying to recruit data analyst instead of data scientist. Data analyst is a person who knows some data mining or machine learning tools, who can solve some well-defined problem with given data set, and also well-defined result format. So the problem is well defined. The data set has been given, and we know what kind of output we need to generate. This guy knows some module components or tools. They use the tools to solve the problem, generate the results. But a data scientist is different. You have to understand the problem yourself. For example, I'll give you one example. I'm currently working on the Smart Shanghai, Smart Xuhui project. Xuhui is a district of Shanghai, the richest district in Shanghai. When I came to Xuhui, the government official provided me with a requirement. They told me we have one road with many dirts, which is very, very dirty. Can you remove the dirts of the road by using your big data technology? We don't really know what this problem is. It's a classification problem, it's a regression problem, it's an anomaly detection problem. We don't really know. And they don't tell you what kind of data you can use. You have to imagine what kind of data you can use, and grab data by yourself, and finally generate result, solve the problem. And another question raised by Beijing government is, if we move some department of Beijing government from downtown area to the rural side, what's the impact to the Beijing's economy, environment, and transportation? Such kind of question is very hard to answer, but that's the question that data scientists need to answer. And you will feel lucky if governments can provide you with questions and problems. In many cases, when we go to some city to do smart cities projects, you ask a government official, what do you need? They don't know. Yeah, that's very typical situation. They typically ask you what you can provide. Then all the case I present here has been invented by ourselves before the government can provide us with real requirement. Then we present our application to them and say, oh, this is good, then you can deploy this one in my city. So that's what data scientists need to do. If we say data analysis is an undergraduate student who should be given a well-defined problem to solve, and then data scientist is a PhD student who would graduate very soon, who need to find the problem, research problem themselves, and to solve the problem by themselves. So that's the difference. So more specifically, the data scientists need to understand the problem very well. For example, if you are trying to solve the transportation problem, you need to know what will cause traffic congestion. And then you also need to know what's a traditional model and algorithm that have been proposed in traditional transportation area. By knowing what people have done, you can learn from their algorithm and design your own model. By learning from existing model, you can know why they cannot work out this problem and why your model is better than them. We cannot expect people from the domain will accept our model if only we have a better performance. You have to tell them why your model is better than them and speak with their own language. So you need to have a deep understanding of the problem itself. And also you need to understand the data itself. not only the format of data, but also the insight behind the data. For example, the GPS trajectory of taxi cabs does not only imply the traffic condition on road segment, but also people's commuting pattern, because we know where people get on a taxi and get off taxi. With the pick up and drop off information of massive taxis, we know the commuting pattern of an area. Then the commuting pattern of people in an area can further infer the function of the area and the environment of the area and also the economy of the area. With the understanding of the insight behind the data, we can solve the problem in domain A by using the problem from domain B. Then you will feel we have a lot of data sets. Data will not be sparse or scarce anymore. So that's the reason we emphasize the data and the problem. You need to also harness the diversity of module, not only machine learning and data management, visualization models. And also need to understand how to use cloud computing platform. So a data scientist is a guy standing on the cloud computing platform, looking at the problem, thinking of the data, combining different modules of algorithm, and deploying this algorithm onto the platform to generate fresh knowledge to solve problem in domains. So that's a data scientist. Okay, so I summarize my talk with few sentences. So first, big data is an end-to-end capability from data collection, data management, data mining, and the visualization and the service providing. It's a end-to-end capability. It's not about how big data is. The key issue is how to fuse the knowledge from different data sources. And in order to do big data project or do urban computing project, we need to have a platform with data management algorithm and storage data management and the machine learning algorithm on different layers. And also we need to know domain knowledge. That's very important. And finally, I believe AI and big data technology is fairly new for spatial temporal data. There are a lot of room and a lot of space to explore. And we expect a better city by using AI and big data technology. That's all for my presentation. Thank you for your attention.